Before we go on to the next kind of function that we'll be able to treat, we need some more fundamental ideas from complex analysis. It doesn't seem like it should be related at all, but we're going to talk about complex integration. And to do that, we're going to go back to the idea of an analytic function. Remember, an analytic function is one that we can represent as a power series. And a singularity is a point where a function is not analytic anymore. So for example, 1 over 1 minus z in a small neighborhood of 0, we can write that as some n greater equal 0, z to the n. So 1 over 1 minus z is analytic at 0. Actually, with a little algebra, you can show that 1 over 1 minus z is analytic everywhere, but at z equals 1. But the idea is representable by power series expansion. And if we look at all the generating functions that we talked about, they're analytic almost everywhere. There's just a few points where they're not analytic. And those are the points where the denominator blows up when it's a ratio, or the square root is a special case that we'll talk about later on. But generally, they're analytic lots of places. So that's why it's important to us. Now, as an aside, I want to start talking about computing with complex functions, because we can do plots that actually are quite illuminating, and I want to start with that. It's not really an aside. It really is the way we're going to talk about the functions. And for computer scientists, it really reinforces the idea of abstraction, that we can write programs that manipulate complex numbers. Some programming languages have it built in, but even if it's not, it's very easy to do. If you're not familiar with object-oriented programming, you can look at one of our introductory textbooks. And this example, we talk about this example in detail, exactly this example, because it's such a good example of object-oriented programming. So we can define with code like this what a complex number is. The first two lines say that a complex number is a real part and an imaginary part. And the next lines define how you create a complex number. If you take a real part and imaginary part, you set those values. And if you have those values, you can define the functions to compute with complex numbers, just according to the basic definitions that I gave. So if I'm a complex number and I want to add another complex number b to my value, then I can take my value as a. That's what that complex a this means, and I can compute the real part by adding a's real part and b's real part, and the imaginary part by adding a's imaginary part and b's imaginary part. And then make a new complex number with that real imaginary part. That's the result of the plus operation. And times has the cross multiply exactly as defined, and we can go ahead and write code for the other operations. And that code will be posted with the website. If you don't do programming, fine, but it's maybe just as easy for you to learn the programming as it is for the programmers to learn the complex. So I hope everybody works with the code as well as with the mathematical abstraction. And so we can talk about the idea of what is a complex function. It's just something that, given a complex number, evaluates and returns a complex number. And so this is an example of code that implements the complex function 1 over 1 plus z cubed. 1 is a new complex number that's got a real part of 1, imaginary part of 0. And then the denominator is going to be, we're going to take that number 1 and add a number to it. That's what the dot plus means. What are we going to add to it? We're going to add z times z times z. So that's 1 plus z cubed. And then we're going to take the reciprocal of that. That's the complex number that we're going to return, 1 over 1 plus z cubed. It takes a little while to get used to this kind of syntax, but not that much. And I think, again, most people will find it easy to look at the code and do simple things with it. And so that's fine. So we can write programs that compute with complex numbers. I just want to mention there's a design choice here, and that is that we treat complex numbers as immutable. That is, every complex number that we wind up computing with is different. Computers nowadays, that seems to be a reasonable way to go. It's the same approach that programming languages like Java use for strings. And what's the point of all this is not just to write code. What's interesting and why I want to do it is that it's also pretty easy to plot complex functions. And we're going to do a particular kind of plot where we do an image. And all an image is a square array of pixels, like everything that you see on the screen is an image. And we're just going to take a 512 by 512 square of pixels, and we're going to give, that's points in the plane, and we're going to give, for a particular complex function, we're going to give every pixel a grayscale value according to the magnitude of the value of the function. If the function's got a high value, it's going to be black. If it's got a low value, it's going to be white, and the gray says how big it is. So that's what this code in here is doing. It's going to give an x and y, which are scaled, the xy coordinates in the image. It's going to create a new complex number, and then it's going to evaluate a function, a given function, at that complex number, compute the absolute value, and actually we multiply by 10 to really emphasize the growth. That's an arbitrary factor. And then we're going to convert that to a number between 0 and 255 to get the grayscale, and then we'll set the color of the pixel, and we'll do that for every one of the 512 by 512 pixels, or whatever size that we set it to. But that's the key. Every point has a color, which is black if the function's high and white if it's low. And this is really simple code. Any programmer will have no trouble with this. And if you're not a programmer, go to our book sites for our introductory courses, and you can work with this code. It's not difficult. So then what we can do is, so this is the example where we implement 1 over 1 plus z cubed. And all we have to do is call this function, a new version of that function, 1 over 1 plus z cubed, and we get a plot like this. This is for 1 over 1 plus z cubed. Now our convention is we'll always draw a 2.5 by 2.5 square. So that's minus 1 over there. And this is square root of 3 over 2, and so forth. So the darkness of the pixel is proportional to absolute value of 1 over 1 minus 1 plus z cubed. So most of the time it's pretty small, unless you get close to something whose cube is minus 1, like minus 1. Or these are what's called the roots of unity, and that's a wonderful part of the lore of complex numbers that I haven't talked about much just for the purpose of room, but those are the numbers that if you cube them you get minus 1. So that's what that plot looks like anyway. Very easy to get a visual representation of a complex function, and what we're really interested in is that this visual representation shows us the singularities, that is the points where it blows up and you can't represent it with the power series, the points where it's not analytic, where the function goes to infinity. There's all kinds of functions. These are just some examples. So this is what 1 plus z to the 5th looks like. And this is a little bit bigger square. If we're not going to be showing the 2.5 by 2.5 square, we'll show that one in white, because sometimes interesting things happen outside of that square. A surprising amount of time, interesting stuff happens right within that square. This is what e to the z plus z squared over 2 looks like. So when z gets positive, it starts to get big. When z gets negative, at a certain point, it starts to get big. Otherwise, it's small. That's kind of what these things are saying. But those values are, those functions are analytic everywhere. That they're going to infinity, but at a reasonable rate. So let's look at the rational functions we've looked at. So 1 over 1 minus z has a pole at 1. 1 over 1 plus z squared has poles at plus and minus I. 1 over 1 minus z to the fifth, those are the fifth roots of unity. This is what the generating function for the number of binary strings with no occurrences of 4 zeros in a row looks like. It's got 4 poles, they're kind of spread out like that. So we get a feeling for at least how big the function is from these kinds of plots. And then this is that other one for set partitions. And we'll look at the properties of these later on. So the idea is that we can, with these plots, we can characterize the functions, and we'll be doing that for a purpose later on. But now let's talk about complex integration. So this is another very fascinating part of complex analysis. It's a simple idea. You just want to define a line in the plane, and you want to integrate along that line. And so like a straight line, it's pretty easy. You just change variables to convert to real integrals. Like if you integrate along that line at x equals 2, then you can pull the 2 out and just do y as it changes, change to x plus iy, and another I comes out. So the 2 comes out with an I because we're changing along the y-axis. Then y squared over 2 from 3 to minus 1 because we're going down. So that's a complex number. That's the value of that integral. So that's a natural starting point. Now but we can add to that an integral that goes in a different direction and make a closed contour. We can do around a circle. We have a lot of variability in terms of trying to define an integral. And some amazing facts is that if you have an analytic function in a region and you have any path of integration that's a loop, the integral is going to be 0. And not only that, relevant for analytic combinatorics, you can get the coefficients of a complex function by complex integration. So that's what we're going to look at next. This is due to Cauchy, and these facts are, again, part of the foundation of a deep and beautiful theory that we're going to take advantage of. So for analytic combinatorics, what we're going to use this for is to get exponential growth for this bigger set of generating functions than the rational, called meromorphic. But let's look in more detail at some examples of integration. So let's say we want to integrate f of z equals z on a rectangle. So we'll just integrate along the 4 lines, just as I did before. So if you're integrating on x, then you can just leave the y part alone and just integrate. In this case, it's minus 6 plus 3i. This next one is the one I did before, which is 2i plus 4. This next one goes the other way. It happens to be at I, so it's 6 minus I. And this other one goes up the other way, turns out to be 4i minus 4. So if we want the integral all the way around that rectangle, we just add those 4 things up together. And so just add these 4, and what's amazing is that we get 0. We had lots of different values. They just, you can check my arithmetic, they all add up to 0. Here's another example. We're going to integrate f of z equals z on a circle centered at 0. So now we're going to hold the radius fixed, and we're going to change theta. So we write our complex numbers in a polar coordinate, z equals r e to the I theta. So then dz equals ir e to the I theta d theta. We plug that in, then we have z dz, so we have ir squared. We got e to the 2I theta d theta. So integral of that is e to the 2I theta over 2I, same sorts of rules as with the reals. Evaluated from 0 to 2 pi, but 2 e to the 2 pi I equals 1, e to the 0 equals 1. And that's from Euler's formula. E to the 0 equals 1, so it's 0. Integral of f of z equals z on a circle centered at the origin is 0. It doesn't matter what the radius of the circle is. So that's interesting. Let's look at another one. What about 1 over z on a circle centered at 0? So integral of 1 over z, again applying, substituting r e to the I theta, z over dz is just d theta. And then I comes out, so it's just dz over z here. All that's left is I d theta. And so that integral is just going to be 2 pi I. Integral of 1 over z in a circle centered at 0 is 2 pi I. So that's examples of integration. So here's another one. Let's say it's z to a power on a circle centered at 0. So again, same substitution, z equals r e to the I theta, dz equals I r e to the I theta. So z to the m is r to the m e to the m theta. Multiply it out, now we have e to the I m plus 1 theta d theta. And now there's two cases. If m equals minus 1, then we get 0. If m equals minus 1, we get 2 pi I, same as before, because all that's left is 0 to 0, 2 pi d theta. If m's not equal to minus 1, then we're going to have the same 1 minus 1 situation that we had before, and we're going to get 0. Even if it's a circle centered somewhere else, say integral of f of z equals z minus s to the m on a circle centered at s, it's going to be, and I'm not going to go through all the steps, it's almost the same as before. It's going to depend only on whether m equals minus 1 or not. So z minus s to the 10th, it's always going to be 0. But 1 over z minus s, it's always going to be 2 pi I. And these two are going to turn out to be important for integrating analytic functions. So that's a couple of more examples of integration. So now the null integral property. So what that says is if you have an analytic function in a region omega in the plane, and you integrate that around any closed loop in that region, then you're going to get 0. And again, for the purposes of this lecture, we're not going to prove this, where this is going to be an axiom, and I'll talk about why we say it that way in just a minute. This is what we saw. If we had f of z equals z, which is analytic, we integrate it around a rectangle, we get 0. Integrate it around a circle, we get 0. Whatever shape you want to make, and go ahead and calculate the integrals, which you can do, you're always going to get 0. Another equivalent way to look at this is if you have one path alpha and another path beta, and they're homotopic, that just means you can deform one to the other, then the integrals are going to be equal. So that is, there's alpha and there's beta, so they start at the same point, and same starting and ending point, but you can deform one into the other. Then the integral around is going to be 0, but if you switch the direction on beta, it's a proof that the integral on alpha is equal to integral on beta. So from the null integral property, complex integration is quite a different thing than for real functions, because you have this property that in a lot of cases, doesn't matter what the path is, you're still going to get the same value. And that's certainly a fascinating and key property. In fact, I've mentioned really the basis of complex analysis that I just glossed over by stating these things as axioms. If you want to see a proof that these things are all equivalent, that's in the appendix of the Blue Book, or a course in complex analysis really is about this. The idea that a function can be expanded in a power series, the idea that it's differentiable, because that limit that defines differentiation exists no matter what direction you go, and the idea that the integral around a closed loop should be zero, those are equivalent ideas, and we actually, in the book actually proves it with this circle of implication. But now what we want to do is we want to take that null integral property, and we're going to use that to help us extract coefficients from an important class of generating functions, and that'll be our next topic. But before we do that, we're going to talk about Cauchy's coefficient formula, which is an application of the null integral theorem. It does exactly what we want. If we have an analytic function, we want to extract the coefficient of z to the n in that function. And this formula says what you do is you take the function, divide by z to the n plus 1, and integrate over any closed loop that contains the origin. It's not difficult to prove. So our condition is that the function has to be analytic in this region omega that contains the origin, so therefore the function's analytic at the origin, so therefore we can express it as a power series at the origin, or just f0 plus f1z plus f2z squared and so forth. So that's the first thing. Now what we're going to do is take the loop and deform it to a small circle centered at 0, or a circle, and as long as the circle's within omega, we're fine. And then just integrate. And then the integral is, we can integrate term by term. So we're dividing by z to the n plus 1, so it's f0 over z to the n plus 1, and so forth. And then fn over z, fn plus 1, times z to the n plus 1, and zn plus 1 cancels out, fn plus 2z, and so forth, like that. So that's the integral. And now if we look at integration example 4, those things are going to be all 0, because we did an integral that said if you integrate z to the n around a circle containing the origin, it's going to be 0 unless the exponent is minus 1. So the only thing that's left, and if the exponent's minus 1, the value of the integral is going to be 2 pi I. So the only thing that's left is f sub n times 2 pi I. That proves Cauchy's coefficient formula. Just a consequence of the null integral of complex integration. So in the context of analytic combinatorics, this is going to lead to the transfer theorems for a much broader class of functions called the meromorphic functions, and that's what we're going to look at next. The idea of complex integration is a deep and powerful idea that's going to be very helpful to us in analytic combinatorics.